Today we explore the full bridge rectifier using this Digilant analog discovery. For this demo, the red LEDs are used as rectifiers, and the Digilant analog discovery has been set to a period of 2 seconds, and we can see the crisscross as each of the diode pairs activates. Our circuit is represented in this schematic, where we have the Digilant analog discovery as both waveform generator and oscilloscope. The output goes to the bridge, where it is rectified. It then goes to the 100 ohm series current limiting resistor, the 3300 microfarad capacitor, and the 220 ohm load resistor. As far as the oscilloscope is concerned, channel 1 is measuring the output of the waveform generator, and channel 2 is measuring the output of the bridge rectifier. It's important to recognize that the analog discovery has fully differential inputs, such that our oscilloscope channel 1 and our oscilloscope channel 2 do not need to share the same ground. In fact, they can be completely isolated as they are in this circuit. Here's a close-up of our circuit. We have 4 LEDs connected in a bridge configuration. This is that 100 ohm resistor. This is the 220 ohm load. This is a 3300 microfarad capacitor, which is connected here across the load. As an experiment, let's remove this rectifier and see what happens. You'll notice that it's turned into a half-wave rectifier where the charging pulse occurs on the peak of the incoming waveform. For our next experiment, we remove the capacitor. We're going to discharge it through that voltage rail, remove the resistor, and then we're going to reinsert the capacitor and watch how it charges in the absence of a load. You can see that it looks like a stair step where each charging pulse gives it a little bit more voltage. Also, as we watch this, we're going to see that the LEDs get progressively less and less bright because there's less current, because the capacitor is charged. Let me move the scope so we can see that better. At this point, the voltage on the capacitor seems steady, and in person I can barely make out that these LEDs are lit, although they may still be perceptible in the camera. Let's reinsert the load, and you'll see that capacitor voltage drop quite quickly, and the LEDs have returned to their original brightness. There is one more thing I'd like to show you before we stop. Take a look at that blue waveform and observe the difference between the peak and the valley, which appears to be about 0.2 volts. Watch what happens when we increase the frequency. This is now 100 Hertz. With the higher frequency, the time between pulsing of the capacitor is much less. Therefore, we don't see the voltage drop as much, so that ripple is considerably smaller. The LEDs appear to be steady, although there may be some flicker in the camera due to the interference with the shutter speed. Although the LEDs are still activating in this crisscross pattern, one pair for the positive half cycle and one pair for the negative half cycle.